Okay, hello everyone. Let us continue the third part of today's course. Okay, in the first part, we have talked to here. Okay, ANN. Okay, we are talking about what is a multi-layer perceptron MLP. Okay, next page. Okay, in this page, here is a graph, okay, or a figure. Okay, let us see this figure. Okay, figure 38, two classes of points. Okay, you can see that there are some blue points, red points here, and some blue points here. And two of the infinitely many linear boundaries that separate them. Okay, you can see that there is a binary here, a boundary here and a boundary here, okay, which separate red points and blue points. Okay, even though the boundaries are at nearly right angles to one another, okay, you can see that these two boundaries, the angle between them are nearly right angles. Okay, that is 90 degrees. The perceptron algorithm has no way of choosing between them. Okay, so next page. Okay, so sometimes strictly to refer to networks composed of multiple layers of perceptrons. Okay, I have introduced what are perceptrons before. With threshold activation, see terminology. Okay, we will see terminology later. Multi-layer perceptrons are sometimes colloquially. Okay, I will introduce what is the meaning of the word colloquially later. Referred to as vanilla. Okay, I will introduce the meaning of the word vanilla later. Neural networks, especially when they have a single hidden layer. An MLP consists of at least 3 layers. Okay, what does a layer mean? Okay, it has a special meaning in deep learning, okay, which I will introduce later. Of note, an input layer, a hidden layer, and an output layer. Except for the input nodes, each node is a neuron that uses a nonlinear activation function. I will introduce what is an activation function later. MLP utilizes a supervised learning. Okay, I have introduced what is supervised learning in chapter 1. If you forget it, please review the handout of chapter 1. Okay, supervised learning technique called backpropagation. Okay, I will introduce what is backpropagation later for training. Its multiple layers and nonlinear activation distinguish MLP from a linear perceptron. It can distinguish data that is not linearly separable. Okay, here it means MLP. Okay, that is multi-layer perceptron. Okay, and I will introduce what is the meaning of linearly separable later. Okay, next, let us look at the theory of MLP. Okay, first, let us look at activation function. If a multi-layer perceptron has a linear activation function, Okay, I will introduce what is an activation function later. In all neurons, that is a linear function that maps the weighted inputs to the output of each neuron. Then linear algebra shows that any number of layers can be reduced to a two-layer input-output model. Okay, in MLPs, some neurons use a nonlinear activation function that was developed to model the frequency of action potentials. Okay, I will introduce what are action potentials later, or firing of biological neurons. The two historically common activation functions are both sigmoids. Okay, I have already introduced what are sigmoids before. If you forget, you can click on this hyperlink. Okay, and this handout will jump to here. Okay, page 62, problem 1. What is sigmoid? Okay, let us go back to the sigmoids. Okay. So why both sigmoids and are described by y of vi is equal to hyperbolic tangent of vi, and y of vi is equal to 1 plus exponential negative vi inverse. Okay. So, in recent developments of deep learning, the rectifier linear unit ReLU. Okay, I will introduce what is ReLU later. Okay, ReLU is a common activation function which is used in deep learning. Okay, it's more frequently used as one of the possible ways to overcome the numerical problems. Okay, what problems? Okay, I will introduce the problems later related to the sigmoids. The first is a hyperbolic tangent. Okay, this function. Okay, tangent h is the hyperbolic tangent. Okay, I will introduce what is hyperbolic tangent later. That ranges from -1 to 1, while the other is the logistic function. Okay, I will introduce what is the logistic function later. Okay, which is similar in shape but ranges from 0 to 1. Here yi, okay, is the output of the ith node, a neuron. Okay, so you can imagine that here is y, and I add a subscript I here, so it becomes yi. Okay, and this is the same, becomes yi. Okay, and vi, okay, here is the vi, and here is the vi. Is the weighted sum of the input connections. Alternative activation functions have been proposed, including the rectifier and the soft plus. Okay, I will introduce what are rectifier and soft plus later. Functions. Okay, more specialized activation functions include radial basis functions. I will introduce what are radial basis functions later. Used in radial basis networks. Okay, I will introduce what are radial basis networks later. Another class of supervised neural network models. Okay, next let us see layers. Okay, the MLP consists of 3 or more layers. Okay, an input and an output layer with 1 or more hidden layers of nonlinearly activating nodes. Okay, since MLPs are fully connected, each node in one layer connects with a certain weight Wij to every node in the following layer. Okay, so we know that here W means weight. Okay, but what are I and J denote? Okay, let us review. Okay, first I means the ith node, that is neural. And what is J? Okay, let us go to a further part. Okay, so here in an output node J, okay, so J means the jth output node. Okay, Wij to every node in the following layer. Okay, next let us look at the learning issue. Okay, learning occurs in the perceptron by changing connection weights after each piece of data is processed based on the amount of error in the output compared to the expected result. This is an example of supervised learning and is carried out through backpropagation. Okay, I will introduce what is backpropagation later. A generalization of the least mean squares algorithm. Okay, I will introduce what is the least mean squares algorithm later in the linear perceptron. Okay. Okay, we can represent the degree of error in an output node J in the nth data point. Okay, training example by Ej of n is equal to Dj of n minus Yj of n. Okay, where D is the target value and Y is the value produced by the perceptron. Okay, so we can know that excuse me, Ej of n is the error in an output node J in the nth data point or training example, and Dj of n, okay, is the target value in an output node J in the nth data point or training example, and Yj of n, okay, is the value produced by the perceptron, okay, in an output node J in the nth data point, okay, or training example. Okay, so the node weights can then be adjusted based on corrections that minimize the error in the entire output given by this equation. Okay, E of n is equal to 1 second times summation J Ej square of n. Okay, using gradient descent. Okay, I have introduced what is gradient descent. Okay, if you forget, you can click on this hyperlink. Okay, and the handout will jump to here. Okay, the solution to problem 35. What is gradient descent? Okay, on page 63. Okay, let us go back to the gradient descent. Okay. Okay, here. So using gradient descent, the change in each weight is, okay, delta Wji of n. Okay, do you remember what is Ji and n? Okay, let us review it. Okay, the meaning of J is the output node J. Okay, and I is, okay, let us see I. Okay, so I is the ith node, and that is the ith neuron. And what is n? Okay, let us see. N denotes the nth data point or training example. Okay, so it is delta. Okay, delta Wji of n, okay, is equal to negative eta. Okay, what is eta? Okay, here eta is the learning rate. Okay, if you forget what is learning rate, I have introduced it later. You can click on this hyperlink, and this handout will jump to the solution here. Okay, to the problem 1, what is the learning rate, on page 40. Okay, so let us go back to the learning rate. Okay, we have seen before. Okay, learning rate. Okay, good, here. So eta times partial E of n over partial Vj of n. Okay, so do you remember what is E of n? Okay, let us review it. Okay, E of n is defined in the previous equation, in equation 89. Okay, it is the error in the entire output given by this equation. And what is Vj of n? Okay, so what is Vj of n? Okay, let us look at search for Vj of n. Okay, so Vi is the weighted sum of the input connections. So we can know that Vj of n is the weighted sum. Okay, in an output node J in the nth data point, that is training example. Okay, then times Yj of n. Okay, so where Yi is the output of the previous neuron. Okay, so you can see that in equation 90. What does this mean? Okay, this means that the change in each weight is equal to Yi of n, the output of the previous neuron, times the partial derivative, okay, which is equal to one element of the gradient, and times eta, where eta is the learning rate, and a negative sign. Okay, why is here a negative sign? Because it is gradient descent. Okay, descent. Okay, which is selected to ensure that the weights quickly converge to a response without oscillations. Okay, we always hope that our algorithm will converge quickly. Okay, not oscillation, not oscillate. Okay. Okay, let us continue. So, the derivative to be calculated depends on the induced. Okay, I will introduce the meaning of the word induced later. Local field Vj, which itself varies. It is easy to prove that for an output node, this derivative can be simplified too. Okay, this equation, okay, let us see. Okay, negative partial E of n over partial Vj of n is equal to Ej of n times phi prime of Vj of n. Okay, where phi prime is the derivative of the activation function described above. So now you can know that phi is the activation function. Okay, which itself does not vary. Okay, because the activation function is a function that we choose. Okay, so it will not vary, or it will not change. Okay, the analysis is more difficult for the change. Okay, in ways to a hidden node, but it can be shown that the relevant derivative is negative partial E of n over partial Vj of n, okay, is equal to phi prime of Vj of n times summation k negative partial E of n over partial Vk of n times Wkj of n. Okay. So, do you remember the definition of these symbols? Okay, let us review again. Okay, first let us look at what is partial. I think you already know this. It is to take the partial derivative. Okay, if translated into Chinese, it is called 偏微分. Okay. So E of n, okay, let us review the meaning of V of n, or E of n. Okay. So E of n is the error in the entire output. Okay, here. Okay, and what is Vj of n? Okay, let us review it. Okay, let us see Vj of n. Okay, Vj is the induced local field. Okay, but what is the meaning of V? Okay, let us review it. Okay, let us search the meaning of V. Okay, here we know that Vi is the weighted sum of the input connections. So Vj of n is the weighted sum. Okay, here in an output node J in the nth data point. Okay, that is a training example. Okay. So next, let us see it is equal to phi prime. Okay, what is phi prime? Okay, so let us see, okay, where phi prime is the derivative of the activation function described above, which itself does not vary. Okay, so we can know that phi, okay, it is 25 minutes. Okay, see you next time. Goodbye.